Okay, for the vector function f of xy equals yi minus xj, we easily calculate the curl of f, and I'm not going to go through that calculation with you. You can verify you get negative 2k. Okay? And most of these partial derivatives are going to turn out to be 0. There are only 2 of them that don't, and they both give you negative k. So you can explore that as you wish. Okay? Curl of f dot n. Now what's the meaning of curl of f dot n? Okay, I should label on here. It's on your document, so you should be aware of it. But this is where we're asked to integrate the curl of f dot n on the unit disk. Unit disk being the disk of radius 1 centered at the origin in the xy plane. So maybe I should say in the xy plane. Okay, well, we've calculated the curl of this function. It's negative 2k. Now, curl of f dot n. Okay, a normal vector to the unit plane would be like the k vector, straight up. Okay, so the k vector is normal, the upward normal. And that upward normal is going to correspond to an integral in the counterclockwise direction around the unit circle. So, curl of f dot n is curl of f negative 2k dotted the normal vector, which is k, and we just get plain old negative 2. So if we do over this unit disk, the integral over the surface consisting of the unit disk of the curl of f dot n dA, we just get the integral over the unit disk of negative 2 dA, and we don't have to do anything tricky at all. We have a constant multiple of the area increment. So we have negative 2 times the integral over the surface of the area increment. The surface is just the unit disk, and we know the area of the unit disk, so we don't have to do any fancy integration to find that area. We know the area is pi, so that we get negative 2 times pi, or negative 2 pi. That's the integral of curl of f dot n on the unit over the surface of the unit disk in the xy plane for this particular vector function. Okay, now for the same vector function, we want to calculate the circulation, the integral of that vector function around the border of the circle. Now we expect that what goes on the interior of the circle is going to be related to what we can get around the border of the circle, because we understand Green's theorem, and if we don't need to be looking at this. We need to go back and understand Green's theorem. And I've talked about that and talked about the connections, so go back and see that if you need to. In any case, okay, the integral of f dot dr around the boundary of the circle, and again, since we use the upward k vector for the normal, we go around the circle in the counterclockwise direction so that the direction of our integral matches what the right-hand rule tells us about the direction of the normal. Okay? And of course you can read the details of why that works, but that's the way we want to think of it. The parameterization for the circle, well, here's the parameterization. To go counterclockwise around the unit circle, we can use a parameterization r equals cosine theta I plus sine theta j. So the dr is, well, it's just the differential of this. Derivative of cosine theta is negative sine theta, derivative of sine theta is cosine theta. So it's negative sine theta I plus cosine theta j d theta. Dr d theta would equal this, so dr equals this times d theta. It's not really an algebraic rearrangement, but it looks like one, and you can safely use it. Okay, so what you understand about the differential, well, use what you understand about the differential, understand it as you will, but this is this is what you have. Okay, so using this parameterization, yi becomes what? Well, the j component of your r vector is your y coordinate, so it's sine theta I. Okay? And x is your I component, cosine theta, so xj is cosine theta j, and of course we have the minus there. This is the value of our vector function corresponding to whatever the value of theta happens to be. And theta runs from 0 to 2 pi, and that's very familiar, so I'm not even going to mention it except just to mention it. Okay, so that's the value of our vector function. What's our dr? Well, there it is, so let's just write it down. Negative sine theta I plus cosine theta j times d theta. And it's, of course, the dot product of f dot dr. We're looking at the component of this vector field that's in the direction of our circle. It's in the direction tangent to our circle. That's what the dot product tells you. Make sure you understand what the dot product is telling you. It's giving you the component of something in some other direction. And there are other factors, but that's the first thing you got to understand. Okay. Well, we do the dot product and we get this. And this is just one. Sine squared theta plus cosine squared theta. And we're integrating with respect to theta. Now, I wrote the limits in the integral 0 to 2 pi here. I didn't write them here because I was running out of room, but let's just go ahead and fill them in here, whether you can read them or not, and maybe you can if you've got good resolution there, a decent sized picture. 0 to 2 pi. And of course we get a negative out here because we have a negative sine squared here, negative cosine squared here. That's just mechanics. So we have a negative of this integral, so it's a negative integral from 0 to 2 pi of 1 with respect to theta. Well, you can do that. You get negative 2 pi. And then we see that this result is the same as this result. Now in class I got negative 4 pi there. Go back to my error warning. When I wrote down the area of the circle, I had a bunch of 2 pi's running in mine, and I wrote down a 2 pi because I wasn't thinking. And I got a negative 4 pi here, but clearly we corrected that. The area of this circle was pi, not 2 pi. So we just got negative 2 pi. Okay, so the integral of the curl of f dot n over the whole unit disk is equal to the circulation around the unit disk of this vector function, which is defined by the integral of f dot dr over the curve bounding the disk. This is an example of Stokes' theorem for a fairly simple surface.